Hello, today I want to talk with you about generalized automorphisms of channel codes. My name is Jonathan Mandelbaum and this presentation was also presented at this year's ISTC in Brest. Let me start with a short overview. First I will start by presenting a short introduction in which I will also motivate this work. Then we are going to discuss the definition of generalized automorphisms of linear codes and then talk about the construction of linear codes with designed generalized automorphisms. At this point we will notice that we require a generalization of the automorphism ensemble decoder to be able to use generalized automorphisms at the receiver side to improve decoding. And then I will finish by providing some results and giving a conclusion. Let me start with a short motivation. In future 6G applications, low latency will play an important role. For example, for the communication of control commands or in an IoT setup. However, for such low latency applications, short block codes are required. Yet, for short block codes, there still exists a considerable gap between belief propagation decoding and maximum likelihood decoding. Here on the right side, I depicted the frame error rate performance for an exemplary 6345 code, therefore a short block code. And we can observe here in orange the BP performance compared to an ML decoder in black. And as we can see here, there's still a considerable gap. However, belief propagation decoding is desired because of its low complexity and easy hardware implementation. The idea now is to use ensemble decoding schemes at the receiver side, which are able to both improve performance as well as reduce latency. And in the special case of an automorphism ensemble decoder, the idea is to exploit knowledge that we possess about the code at the receiver side in form of automorphisms. Ensemble decoding schemes are well studied in literature. Their idea is to exploit or to generate diversity at the receiver side to improve decoding. Here on the left side, I depicted an automorphism ensemble decoder as introduced by Geiselhardt et al. A received word Y is permuted according to some sampled permutation in each of those paths, yielding a different noise representation at the input of each decoder. Therefore, due to the different noise representation at the input of each decoder, one may be able to successfully decode when other one fails. After decoding, we have to undo the permutation, therefore undo the automorphism, and then choose the best candidate among all those estimates by performing an ML in the list decision, yielding the estimate of the full ensemble decoding scheme. Also, other ensemble decoding schemes as the multiple basis belief propagation decoder often exploit the automorphism group. In the case of the MBBP, it's not by using them during decoding, but in the process of constructing different parity check matrices that then are used for decoding. Our approach now will be as follows. We are going to generalize the definition of the automorphism group and then also discuss a construction method of codes with suitably designed automorphisms for automorphism ensemble decode, or to be more precise, suitably designed automorphisms for a generalized automorphism ensemble decoder. A starting point of this work was that we noticed a difference in the definition of automorphism group in classical coding theory compared to linear algebra. In classical coding theory, the definition of McWilliams-Sloan is the most prominent one and depicted here. Here, the automorphism group is defined as the following set of mappings, which we name scale permutation, because we have here this factor A, which is a non-zero element from our field, and P is an element from the symmetric group, therefore a permutation, and we can see that A simply scales this permutation. And most importantly, the automorphism group here consists of all self-mappings that are permutations or scaled permutations. However, in linear algebra, the definition is much more general. Here, the automorphism group consists of all linear bijective self-mappings. Therefore, all scaled permutations that are self-mappings are contained within this definition, and therefore the definition in linear algebra incorporates the definition that was most prominently used in coding theory. And our idea is now to exploit this more general definition to improve decoding. To do so, we're going to analyze the generalized automorphism group of linear codes, and to this end we consider a linear code which can be fully defined by a parity check matrix H, and we assume that this parity check matrix is of full rank just for simplicity of the derivations. And now our approach is as follows. We start by considering a linear bijective self-mapping tau from Fn to Fn, therefore on a larger vector space, and later we are going to restrict it to be a self-mapping on our code space. A linear bijective self-mapping tau can be represented by a transformation matrix T, which is in this case regular or non-singular, and T is an automorphism of our code if and only if this following condition holds. Therefore, if we have a code word, therefore X lays in the null space of H, it must still lay in the null space of H after applying the automorphism T to it. Therefore, we want to find all matrices T that leave the null space of H unchanged under right multiplication, and then we have, if we are able to find all those matrices T, we are able to find the automorphism group or the generalized automorphism group of our code. And to formalize it, we want to identify the following set T, which consists of all non-singular matrices T, therefore matrices from the general linear group that leave the null space of H unchanged under right multiplication. To obtain or to identify all those matrices, we first apply or transform our parity check matrix by Gaussian elimination into a simpler form. Gaussian elimination here we perform on the columns can be represented by the right multiplication with a matrix A, and by applying this Gaussian elimination we are able to obtain H tilde, which has the following form, possessing an identity matrix on the left side and an all zero matrix on the right side. This matrix A here is named code characterization matrix because it fully characterizes our code. At this point, notice that the code defined by H tilde here is very easy to describe because it only consists of all unit vectors with entries in its last entries. And then it's easy to check that the null space, and therefore the code defined by H tilde, is unchanged by multiplication with any matrix set of this following set, where it's important to notice that we have a zero block in the upper right corner and a non-singular matrix E in the lower right corner. And now we want to present the following theorem. Therefore, by now sampling any matrix of the following form and conjugating it with matrix A, Therefore, by left multiplication with A and right multiplication with the inverse of A inverse, we can obtain the matrices T that leave the null space of H unchanged under right multiplication. This brings us now to the construction of linear codes with designed automorphisms. To this end, we exploit the fact that the inverse code characterization contains the parity check matrix H in its first n minus k rows. Therefore, if we know A inverse, we know the parity check matrix H, and it is known that a linear code is fully defined by one of its parity check matrices. And our approach now is to find for a given matrix T that we want to be an automorphism of our code, a matrix A and Z, such that the following condition holds, because then we know that T is an automorphism of the code defined by the inverse code characterization matrix. And we noticed that the Frobenius normal form f of T, which has the following structure consisting of smaller blocks arranged on the main diagonal, sometimes is of the required form of this set. Therefore, it possesses the 0 block here in the upper right corner, and the matrix E here in the lower right corner is of full rank. If this is the case, then we can use F as a possible matrix set, and therefore use the change of basis matrix to the Frobenius normal form as our inverse code characterization matrix, and therefore we are able to construct a code that possesses T as an automorphism. To formalize this a bit more, now we want to construct a C and K code with a designed automorphism T. To do so, we sample a matrix T with some desired properties. Later we are going to discuss which properties are desired. Then we determine the sizes Di of the sublex in the Frobenius normal form, the one on the main diagonal, which can be done by simply solving a set of linear equations. Afterward, we check if we can arrange those subblocks such that F is an element of the set, therefore possesses the 0 block in the upper right corner. To evaluate this, we propose the following criterion. If there exists a subset I of the indices of the subblocks such that the sizes of the chosen subblocks sum up to k, then there exists an ordering of the subblocks yielding a 0 block in the upper right corner of the required size, and therefore we are able to calculate a Frobenius normal form of the desired structure, of this structure. So if we are able to do so, then we calculate the change of basis matrix to the Frobenius normal form, and also can calculate the Frobenius normal form. Then we can extract the parity check matrix, which we denote as HC for H constructed from the inverse code characterization matrix. We have to highlight that at the moment we have still to perform a heuristic optimization of the parity check matrix, because in this design process desired properties for the parity check matrix are not yet considered, and therefore we try to find such an optimized parity check matrix by minimizing the number of 1 entries or remove 4 cycles such that BP performance is improved. This brings me to the next point, the generalized automorphism ensemble decoding. The generalized automorphism directly generalizes the automorphism ensemble decoding. Note that in this case we are going to need a different preprocessing rather than directly applying the permutation to the received sequence Y, because a preprocessing in the real value domain is going to be required. After the decoding, we can still simply apply the inverse automorphism to the hard decision and still choose the best candidate with an ML in the list rule. Notice that until now, all considerations hold for an arbitrary field. Now, for simplicity, we confine ourselves to binary codes. However, all those derivations or observations are also valid for different fields if we adapt them suitably. In binary domain, an automorphism is represented by a multiplication with t. Therefore, if x is a valid code word, the multiplication with t yields x tilde, here denoted as x tilde, which is again a valid code word. And notice that each entry of x tilde is just a binary summation of x according to rows of t. Therefore, we have a binary summation, which we also know from the check node update in a belief propagation decoder. Therefore, we are able to show that to mimic the effect of the automorphism t at the receiver side, we have to pre-process the bitwise LLRs using a box plus summation as depicted here. However, it is known that the more values participate in the box plus summation, the lower the magnitude of the outgoing LLR messages, and therefore the information is lost in the pre-processing, and therefore we want to use automorphisms with small so-called weight, and therefore we introduce the weight over permutation delta t, which is the number of non-zero entries of t minus n. And therefore, as we saw in the construction, we are looking for desirable properties, one being now that we want to construct codes with automorphisms or generalized automorphisms that possess a weight over permutation close to 0. The best case is still a permutation. Therefore, if we look, if we construct a code, usually we would construct a code with a certain permutation automorphism group. However, later we're going to see that if we look for automorphisms of existing codes, the more general definition will also be helpful. This brings me now to the results. I was able to construct different codes with the proposed construction method here with different block lengths and different information bits, lengths of number of information bits, and we can see that the minimum distance is often comparable to the reference code. The reference code C1 and C2 are taken from web page code tables, where the reference code for C3 and C4 are a BCH code and a CCSDS code respectively. To assess the performance, we perform Monte Carlo simulation using an AWN channel with BPSK modulations, and all BP decoders perform normalized min-sum decoding. Also, I want to highlight the notation GID P BPL. P denotes the number of paths the ensemble decoder possesses, and L denotes the maximum number of iterations each BP decoder in the path is allowed to perform. Here I want to show you the results for the code C1 that we constructed with of length 3924. This code was designed to possess a permutation as an automorphism. Therefore, our matrix or our mapping T here possesses weight over permutation 0. Also note that given one designed automorphism, we are able, due to the closure under multiplication, to find more automorphisms that we can exploit to improve decoding. Here we have depicted the frame error rate over the B over N0. In orange, we have the BP performance of a plain BP decoder performing a maximum of 30 iterations. In black, we have the ML performance of our constructed code compared to the ML performance of the reference code in blue. And we can see that in this case, our constructed code has a better ML performance than the reference code. And now we're going to take a look at an equal complexity and lower latency latency generalized automorphism ensemble decoder. In this case, because it's the code processor, we use permutation automorphisms, the GAED simply becomes an AED. And we can see that compared at equal complexity, however lower latency, BP decoder, the GAED is able to outperform the BP at a frame error rate of 10 to the power minus 3 of about 0.6 dB. If we now increase the complexity, therefore by introducing a BP90 and comparing it with a GID3 BP30, we can observe that in this case still the GID outperforms the equal complexity BP decoder, and also it's interesting to highlight that the GID3 BP30 possesses the same latency as the BP30 but significantly outperforms the BP30. Still, we can further increase the complexity while keeping the latency constant by introducing a GID7 BP30, which further improves the decoding performance. Next, I want to present you the simulations result for the code C3 with block size 63, therefore a bit longer code. This code was designed to possess a generalized automorphism with weight 5 over permutation. As I mentioned before, usually if you construct a code, you try to construct it with a certain permutation or automorphism. However, in this case, we constructed a code with a generalized automorphism to be able to prove that generalized automorphisms may be able to improve decoding. And here we can first see the ML performance of the reference code, BCH code, as well as the BP performance of the reference code. One can see that the ML performance of the BCH code for higher SNR outperforms the constructed code. However, the BP performance of both codes are comparable. And now, by using a GID3 BP10, therefore at equal complexity and reduced latency, we are able to outperform the BP30 of about 0.2 dB at a frame error rate of 10 to the power minus 3. This serves as a proof of concept that the generalized automorphisms may indeed be used to improve decoding, and therefore this significantly enlarges the search space for suitable automorphisms to improve decoding. Also here I depicted the performance of a GID3 BP30, therefore equal complexity to the BP30, and in this case we are able to outperform it of about 0.4 dB at a frame error rate of 10 to the power minus 3. This brings me to my conclusion. We introduced a new definition, or a more general definition, of the generalized automorphism group of channel codes, which is inspired by the definition in linear algebra. Then we also presented a code construction method of linear codes with designed sparse automorphisms, therefore enabling us to investigate how different automorphisms or codes with different automorphisms behave in an automorphism ensemble decoding to better understand its concept. Then we also further generalized the automorphism ensemble decoder to the generalized automorphism ensemble decoder, such that generalized automorphisms can be used at the receiver side to improve decoding. In this setup, we discussed the importance of choosing good automorphisms. One important KPI in this case is the weight over permutation, because a certain weight over permutation leads to information loss. And to again highlight it, we have proven the concept that generalized automorphisms may indeed be used to improve decoding and therefore significantly enlarging the search space for suitable automorphisms to improve decoding. This brings me to my end. If you have any questions, please leave them in the comments or contact me, and thank you for your attention.